Oh, okay. All right. So we're going to do something a little different. Um, so what? So we were on chapter 14, and so we're not going to finish 14. Now 14 was like on the single transistor, and now the book author told me to follow a different type of sequence of chapters than what is typically followed for 3700. And so Jaeger told me to follow this and try to get to 17. And so in order to do that, we're going to finish out, well, we're going to skip the rest of 14. I want you guys to read it. but but we're not going to really dive deep into it and study it, but do read it just for your information, just so you'll be somewhat familiar with it. And so today we're going to start in chapter 15, and then we're going to do 15 and then 17, and that's what Jaeger suggested we follow. And the reason I think he suggested that is because even though this stuff is important, the stuff in 15 and 17 is seems to be more important and more practical and used more often than these things. Although these things right here are the building blocks of 15 and 17. Okay, and you'll see that too. Okay, but that's just so you'll know, because otherwise we've been following along, every single section of every chapter. So since then, okay. So review. So for the last lecture, we looked at the common collector amplifier and common drain amplifier. We summarized a certain number of their characteristics, and we looked at the similarities. So they both provide a gain of about 1. They both have high input resistances, low output resistances, and both can handle relatively large a range of signal levels. The difference is the BJT has a finite input resistance and also gain beta 0. The FET usually achieves a high input resistance due to the high gate resistance right here. Now the BJT can usually reach low output resistances due to the high transconductance, and the FET has infinite current gain. So differences and similarities right there. So this is where we had left off. So that was a follower circuit. That was a common collector and common drain amplifier. Okay, so these are the sections that we're skipping right here. So read those when you get a chance. Yeah. So now, okay. So let me. I want to show you guys something dealing with like the BJTs. So one thing that, and I just got this information quite recently from Wilimowski, who just retired. He's a professor here. And let me see if I can enlarge this right here. And so this is, these are interesting things that haven't been published yet. But what he was working on was trying to use the BJT to do some mathematical processing that's typically done with digital components. And so he never got around to publishing these things, and this is like one of the last things he was working on before he retired. But he gave this to us because what we were trying to do is do some really fast feedback for MEMS devices, right? And the kind of feedback we wanted to do was we wanted to look at the state of the MEMS device and then feedback a signal that had been processed from its state. So we looked at the capacitance, because for MEMS, unlike circuits, the capacitance of MEMS is always changing. And the capacitance tells you where the MEMS device is, its trajectory. So we have to look at that capacitance, and then when you have capacitance that's changing, basically you have current moving onto a capacitor and moving off. And that current that's moving on and off is proportional to the displacement or the velocity of what the MEMS device is, how that's moving. So that's the current. and there's things that you can do that current and feed it back. And the reason why you want to try to avoid digital, if possible, if you want to do really fast feedback, is because we've seen this in class, right? When you want to go from the analog domain to the digital domain, there's a time lag, right? Now there was the flash A to D converter, and that was like in the nanoseconds, and that's pretty good. But typically the converters are like maybe anywhere from 1 to even 3 orders magnitude slower than that. So going from analog to digital takes some time. The digital's very fast, but then going from digital back to analog is very slow. So the input and output those conversions from digital to analog, from analog to digital and digital to analog, those are the things that messes up your delay, and it gives you some latency in feeding back your signal. But if everything is done in the analog domain, you can get down to single-digit nanoseconds of feedback. So, wait. Yeah. So anyway, here's like just some examples, right? Where, and remember before we were looking at places that you can put the input for a BJT and places where you can take the output. And so that's what Wilimowski was dealing with, and also looking at the characteristics of how these things behave. And what you can do is come up with some really interesting mathematical types of relations between the currents going in and out of these BJTs. And you just have them in different combinations. And this is just a start, and there are probably a lot more that could possibly come out of this. I don't think this list is exhaustive, but this is where he started off. So yeah, I'll give you guys a slide, just if you're interested in this kind of thing. I mean, if you're ever trying to do some interesting processing, right? So so that's the device right there. Oh yeah, and just to be clear what we were trying to do, just so it'll make sense to you. So these right here are the capacitors, right? So they're like little fingers that overlap. So this whole thing is moving back and forth like this. And so everything in blue is static. Everything in blue is not moving. It's like anchored to the chip, the substrate. Everything in red, like that's anchored, but everything in red can move back and forth. So these are like little flexures that allow this thing to oscillate back and forth like that. Okay, and so these are sensors. Not only are they sensors, but they're actuators, because if you could apply a voltage across these two guys, then you generate a force that causes it to engage. Okay, so they're both sensors and actuators. And so what we were trying to do is, well, here's the mechanical mass, mechanical damping, mechanical stiffness. And what we're trying to do is create an electrical mass, electrical damping, and electrical stiffness using feedback, right? Because if you feedback a force that's proportional to acceleration that you're sensing, or proportional to velocity, or proportional to the displacement, then you can make this device think or behave like it's actually heavier, or it's in a vacuum even though it's in air, or it resonates like a nanostructure even though it's a microstructure. You know, you could change its behaviors, its characteristics, and things like that by doing, if you have really fast feedback, that is. But anyway, that's just an example where single transistors are actually useful. But again, that's we're going to get into even things that are even more common. Okay, so that gives us a segue into chapter 15. So this is going to be design of differential amplifiers and operational amplifiers. Okay, so we'll start off with this one right here, differential amplifiers. Okay, so so the coupling capacitors, now discussed in chapter 14, where we just left off of, they actually limited the low frequency response and of these amplifiers, and it prevented their application as DC amplifiers. So that's one of the downsides. Okay, for an amplifier to provide DC gain, the capacitors in series with the signal path must be eliminated. Okay, and here's a few things in series, right? So this is like a three-stage, right? You have a CS amplifier right here, you have an EC amplifier right here, and a CC amplifier right there. And the capacitors, the C1, C3, C5, and C6, these right here are the ones that need to be eliminated, right? And that, of course, makes sense because what we talked about last time, these right here are DC current blockers, right? So you want to eliminate those in these situations. And now if these things are eliminated right here, then what that is called a DC coupled or direct coupled amplifier. Okay. Okay, so the direct coupled design can also eliminate additional resistors that are required to bypass, to bias individual stages in AC coupled amplifiers. So that can actually reduce cost. So that's another benefit. So the DC coupled differential amplifier is one of the most common building blocks for analog design. These differential amplifiers appear in almost every analog integrated circuit. It forms the heart of operational amplifier design in most DC coupled analog circuits. And although the differential amplifier contains two transistors in a symmetrical configuration, it is usually thought of as a single stage amplifier because they have certain benefits if you consider them to be matched, and that's what we'll be doing in this lecture and others. It has characteristics similar to those of a common emitter, CE, and common source, CS amplifiers. Okay, so here are two examples of a bipolar right here and an MOS type of differential amplifier. And you can see that they're actually symmetric, about the vertical axis right here. Okay? So they have two input terminals, V1 and V2. Here's V1, here's V2, the input terminals, V1 and V2. The differential mode output voltage, that's the VOD right here. That's the voltage between the collectors or the drains. Okay, so you have this VC1, VC2, the difference between that voltage, or the drains, VD1 and VD2, the difference between those. So the ground reference outputs between the collector or drain to ground are these VC1, VC2, VD1s, VD2s. So this is in reference to ground right here. So this is in reference to the two. That's in reference to the grounds. Same over here too. Now the symmetrical nature of these things provide very useful DC and AC properties, and the book talks about that people will try to get these as symmetric as possible. So typically that can happen, or you get the best results when you do your integrated circuit type of processing, because that's when you can really fine tune the performance, the parameters, and the characteristics of how things behave. Okay, so for different input signals, the differential amplifier behaves as an inverting or non-inverting amplifier. Okay, for common input signals, it will reject them, which is good. Also, ideal performance is obtained only when it's perfectly symmetric, and we're going to assume it is for most cases. And it is matched if both sides have identical parameters and characteristics. Okay, and what I mean by characteristics is how these parameters behave. Okay. Okay, so let's find the Q point of the transistor. Okay, so this quiescent operating point of the bipolar differential amplifier is found by setting both input voltages, the V1 and V2, to 0. So here's the the input voltages, V1 and V2. We'll set those to 0 by just grounding them out right there. So that's the first step. Okay. Okay, then after you do that, then a few things pop out of that. And what you get is that the VBE1, VBE2, we'll set those equal just to VBE. Those are all the same now. So we're talking about these right here. So this was VBE1, that was VBE2, and now they're identical because these are both grounded right here. So the voltage going from here to here, that's shared. So that voltage right here is going to be common to both. These are both grounded, and so that's going to be common to both. And that's why you could say that these two things are identical. Now, if the bipolar resistors Q1 and Q2 right here are also matched, then their terminal currents are identical. And that's this IC1 and IC2. So we're talking about these currents right here. Those currents are also matched. So we're just going to call those ICs. Okay. And that also means that these currents are matched right here. The IE1, IE2, we'll call it IEs. That's the currents right here coming out this way on both sides. Those are matched. And then also the IBs are matched. The currents going in here are also matched because of that, right? And that's just due to KCL, conservation of matter. And also these voltages right here are also the same right there. Okay, so that's where we get this situation right here between those two voltages. Okay, now you have these gains right here. You have the current gain, and that's IC over IB, the ratio between these right here. You have this other current gain, A alpha, and that's IC over IE, that over that. This relation right here comes out of that, and that's due to KVL. Like you have your VBE, that's this voltage. You have 2 IE/RE, and that's because you have these two currents going in this direction. So that's going to be your voltage drop across here. And then you have your voltage VEE right there. So that's like going around this loop right here. Okay, that's KVL around that loop. And now I'll just sum to 0. For this right here, this IC is equal to alpha IE. That's from this relationship. And this IE is equal to this. So you have, well, basically, I guess it makes more sense if you put this 2 right here. So 2 IE is equal to this voltage difference over this resistor right here. So the voltage difference between here and here across this resistor has to do with the 2 IE going through that resistor. So that's where that's from. This right here, another KVL for this. This is this VC2, like for this one. It's also the same for that one over there. VCC minus the ICRC. So VCC minus the current going through here, which is IC and RC. That voltage drop is that resistance. I mean that voltage right there. Now this right here, this VCE is just the difference between these two voltages. And this one is just like this one right there. Okay, but just for the other side. Okay, so that's the relationship. Again, this stuff applies here if we're going to assume that these things are symmetric and they're matched for their parameters and also their characteristics. Okay. So the bipolar differential amplifier, it also has some distortion characteristics too. So this has to do with some stuff in chapter 9. Now we started off in chapter 10. So I'm going to assume you guys had chapter 9, right? Do you guys, like in Digitron, did you guys end on chapter 9? Yes, no? Okay. No? It's about this stuff right here. So, okay, so does this equation look familiar to you guys at all? Okay. Okay, okay. It, so it was probably derived in chapter 9. So if you want to find out how they get this, look back at chapter 9. Okay, so we'll take it from this point and assume that that's correct. All right. So we're going to look at the difference between the collector currents. Okay, and then we'll do this IV characteristic. You know. To compare the two. So this right here is the difference between the collector currents. And as you can see, it looks like this is 2 IC tangent H. It's just like this hyperbolic tangent VID over 2 in a thermal voltage right here. And this VID is this right here, VBE1 minus VBE2. This right here is transconductance. So we haven't seen this in this class, but in the last class, Digitron, that's the transconductance of the differential pair. GM is what we've been dealing with. That's the transconductance of a transistor. Okay, and these right here, these values, that's the VBE plus VID divided by 2. This right here, VBE minus VID divided by 2. Okay, so let's take it from here, from chapter 9, and we'll take this and do a Maclaurin series. Okay, and remember that's just a Taylor series about 0. So we're going to take this right here. So we have your 2 IC, and then we take this right here. So doing a series on this right here, this tangent H, is just like this. Now, what's really interesting is that it's going in powers, in odd powers. You can see that. The nice thing about that is that that actually eliminates any distortion that are due to the even powers. So that's quite interesting. So, and also, if you want to do, now we're also we're usually concerned about about trying to linearize things. So for linearization, what you want to do is you want to assume that this third order term, sometimes it's the second order term, but in this case, the next one is the third order term. Here's the linear term. You want to make sure that this term right here is 10 times smaller or more than this term right here, the linear term. So if that's the case, if this is 10 times or more smaller than this term, then you can get rid of this term and all the ones that follow. And then you can just linearize around there. And here's the criteria for that right here. The criterion is, so basically, if you set that to be a 10th smaller than this, and to solve for VID, you get this inequality. That VID has to be less than or equal to this expression right here. Our VID has to be less than or equal to 27 millivolts. Okay. Now here's, this is what the transfer characteristic looks like. So here is the difference between these collector currents. So collector current is on this axis, and it's sort of like normalized a little bit. And the VID, which is the difference in VBEs, they're on this right here, this axis. So this transfer characteristic, this transconductance right here of the differential pair, it is the derivative of this with respect to VID. So the derivative of these currents with respect to VID. So this right here is the difference between those collector currents. That's what this plot is. And see how it's pretty flat right here, and then around between this range and this range, that's where things start to change and happen. Okay? And so the derivative of this is this plot right here. Okay? So the slope here is 0, so that's why this is 0. Right here. And then as the slope increases this right here, you have this sort of like inflection point right there. Um, I'm trying to wonder why. Okay, so yeah, okay. So this inflection point, that's the point of maximum slope. So that's what we have up here. So you have the maximum slope up here. And then what happens is that, so the slope gradually begins to increase. You have the maximum slope, and then it begins to decrease again as it goes up here. That's why this goes up here like that, it maxes out, and then starts going down like this. And then we have zero slope again, so that's why this value right here is 0. Yeah, okay. So this is what you'll use to look at the Q point, where you're going to set your Q point at, is what's happening with your transconductance, okay? And, oh, and it says here, for this VID, remember this right here is a VID, so this, for this VID being, the magnitude of that being greater than 6 of your times VT are 150 millivolts, the currents no longer change as VID changes, right? Which is kind of interesting. So, and you can see that right here. So if you're out here, if your VID changes from here to here, you see that the currents, the difference in those currents don't change at all. They stay the same. Okay, so here's like the interesting thing that happens between these two values. Okay, so so now that we have the Q point information, let's use small signal analysis to characterize the voltage gain and input and output resistances of the differential amplifier. Okay, so the AC analysis of the differential amplifier is simplified by breaking up the sources V1 and V2 here and here into equivalent differential mode. This is the differential mode right here, and common mode. That's supposed to be IC right here. So here's the differential mode input, the VID. That's just V1 minus V2. And the common mode, which we saw before, the common mode is the average between the two. So the difference between the two and the average between the two. And graphically, that's represented by converting this to something like this, where here's the average and here's the differences between the two. Okay. So I hope we finish up. So the total input voltages can be written like this. So where that V1 is the VIC plus that, V2 is VIC minus this right here. Similarly, the differential mode for the output, the differential mode output and common mode output, they could be written like this. So it's very similar to what we have here. And the relationship between the outputs of the differential and common and the inputs of the differential and common is this matrix right here, where you're just doing your matrices like arithmetic like that. This right here is the differential mode gain. This right here is a common mode gain. These two are often 0 if it's matched, but this is the common mode to differential mode conversion gain, this right here. And this is a differential mode to common mode conversion gain right here. So that's what these are. Now, so what we'll do coming next in the next lecture is we'll take off from here, and then we'll use that to further characterize these types of amplifiers. Okay, so it says here for the rest of the chapter, we're going to assume that the transistors are matched. That means that these are 0 if they are matched, unless it's otherwise stated. And we'll use this relation to fully characterize the signal properties of the differential amplifiers, and we'll be finding the voltage gains and input-output resistances of the amplifiers. Okay, that's it for today. See you guys tomorrow. I mean, not tomorrow, but Friday.